Hi again, and welcome to Embedded Systems course, Prototyping with Arduino Uno. In today's topic, you are going to learn how to work with servo motor by controlling its speed and direction. Also, you will learn how to create a program to manipulate a 7-segment display and understand the main difference between a common anode and a common cathode design. More importantly, you will learn how to control several components almost simultaneously, or should I say, multitasking, by using the millis function instead of a delay. At the end of this lecture, you should be able to create your own prototype that controls a 7-segment display, a servo motor, LEDs, and a switch simultaneously, without using the delay function. So, let's begin. In this activity, we will be needing the following materials: a 7-segment display, 2 LEDs, 9 220 ohm resistors, a tactile switch, a 10 kilo ohm resistor, a servo motor. I'll be using an SG90 microservo, a couple of connecting wires, breadboard, and your Arduino Uno. Let's start with the 7-segment display. The 7-segment display consists of 7 LEDs arranged in a rectangular fashion. Each of the 7 LEDs is called a segment because when illuminated, the segment forms part of the numerical digit to be displayed. An additional 8th LED is sometimes used within the same package, thus allowing the indication of a decimal point when 2 or more 7-segment displays are connected together to display numbers greater than 9. Each one of the 7 LEDs in the display is given a positional segment with one of its connection pins being brought straight out of the rectangular plastic package. These individual LED pins are labeled from A through G, representing each individual LED. The other pins are connected together and wired to form a common pin. So, by supplying voltage to the appropriate pins of the LED segments in a particular order, some segments will be light and others will be dark, allowing the desired character pattern of the number to be generated on the display. These then allow us to display each of the 10 decimal digits 0 through 9 on the same 7-segment display. The display's common pin is generally used to identify which type of the 7-segment display it is. Since each LED has 2 connecting pins, one called the anode and the other called the cathode, there are therefore 2 types of LED 7-segment display called common cathode and common anode. The difference between the 2 displays, as their name suggests, is that the common cathode has all the cathodes or the negative pins of the 7 segments connected directly together, and the common anode has all the anodes or positive pins of the 7 segments connected together. In a common cathode display, all the cathode connections of the LED segments are joined together to logic 0 or ground, and the individual segments are illuminated by applying logic 1 or high signal via a current limiting resistor to the anode of the particular segment A to G. However, in a common anode display, all the anode connection of the LEDs are joined together to logic 1. The individual segments are illuminated by applying a logic 0 or ground signal via a suitable current limiting resistor to the cathode of the particular segment A to G. Depending upon the decimal digit to be displayed, for instance, to display the numerical digit 5, we will need to light up 5 of the LED segments corresponding to A, C, D, F, and G. And this is how the digits from 0 through 9 can be displayed using a 7-segment display. Thus, we can produce a truth table giving the individual segments that need to be illuminated in order to produce the required decimal digit from 0 through 9. For this illustration, I will be using a common cathode 7-segment display, so it means I will be connecting the common pins of this 7-segment display to the ground. However, if you are using a common anode 7-segment display, the common pins must be connected to the positive 5-volt supply. Although a 7-segment display can be thought of as a single display, it is still 7 individual LEDs within the single package. And as such, these LEDs need protection from overcurrent. So, this current must be controlled and limited by a safe value by an external resistor to prevent damage to the LED segments. I'll be connecting a 220 ohm current limiting resistor to each individual segments. Now, a huge question is that, How do you know if what you have is a common anode or a common cathode 7-segment display? Well, unlike with a single LED, wherein you can easily spot the anode and the cathode pins, in a 7-segment display, we have to test it. So, for this example, if I assume that this is a common anode, the common pins must be connected to the positive 5 volts. And to test each individual segments, I am going to connect any of these segments to logic 0 or ground. If it emits light, then we are correct. If it doesn't, it means what we have used is not a common cathode but instead a common anode 7-segment display, and therefore, we need to reverse the connection by placing the common pins to the ground, and each individual segments now requires logic 1 to emit light. In this illustration, you can see that segment B emits light. So, if we want to, let's say, display digit 4, then segments B, C, F, and G must be supplied with logic 1. Likewise, to display decimal number 7, segments A, B, and C must be supplied with logic 1. Of course, it is not practical that we have to manually connect each segment every time we want to change the display. Well, commonly, 7-segment displays are driven by a special type of integrated circuit also known as 7-segment decoder. There are many binary coded decimal or BCD to 7-segment decoder ICs available, including the very popular TTL 7447 and 7448 to drive both the common anode and the common cathode respectively. But for this demonstration, we are going to use 7 of the Arduino's digital pins and write a program that acts as a decoder circuit to drive the 7-segment display. For this, I will be connecting pin 13 to segment A, pin 12 to segment B, pin 11 to segment C, pin 10 to segment D, pin 9 to segment E, pin 8 to segment F, and pin 7 to segment G. Let me replace these wires in the common pins with this small connecting wire so it doesn't block the view of our display. In the setup function, I'll create a for loop starting from I is equal to 13 down to I is equal to 7. Then I'll use this variable I to set the pin mode of pin 13 to pin 7 as output. In the void loop, if I want to display a decimal number 4, I can simply do this. As you have noticed, segments B, C, F, and G are supplied with logic 1. These are the only segments that should emit light and will cause digit 4 to be displayed. Let's upload the code and see what happens. Although it works, but if we are going to display digits 0 through 9 with this kind of coding approach, it will be very inefficient and hard to manage. Let me modify this code and I will declare an array and give it a name, digit 4. I'll set its content to 011 0011. This should correspond to segments A, B, C, D, E, F, and G for index 0 to 6. And now, in my void loop, I'll replace this entire bunch of code with a single for loop, similar to the void setup on how we set the pin mode of pin 13 to pin 7. The main difference is that I'll be using digital write function to write to each pin starting from pin 13, which is segment A, the array content that corresponds to this segment. So, for pin 13, I need to access index 0. For pin 12, I need to access index 1. For pin 11, I need to access index 2, and so on. And with that, I'll use the array digit 4 and access each element pointed by index 13 minus I. It only means that, as it loops through the values of I from 13 down to 7, this code is trying to access index 0 to 6 instead. Let's try uploading this one to see if this new code will still accomplish the same thing of displaying digit 4. And there you have it. Let me copy-paste this array and change it to digit 5. I'll modify the corresponding segments A, C, D, F, and G to emit light. After displaying digit 4, I'll pause for a second, and then copy-paste this entire code block and change the array being accessed to digit 5. Let's upload it again. And as you can see, digits 4 and 5 are being displayed in a loop at 1 second interval. But even though we have used an array for this, you will notice that these similar lines of code will still be repeated at least 10 times if we are going to display digits 0 to 9. So for that, I'm going to modify our data structure one more time and use a two-dimensional array instead. I will call it digits with 10 rows and 7 columns. This represents 10 digits for the rows. Each digit has 7 columns that represents the segments for each digit. So for digit 0, only segment G is turned off. For digit 1, only segment B and C are turned on. For digit 2, only segments C and F are turned off. For digit 3, only segments E and F are turned off. And if we refer to the previous truth table, we can complete this 10 by 7 two-dimensional array of digits. I no longer need these single-dimensional arrays. Similarly, I'll remove this duplicate for loop that displays digit 5. And then, to access a two-dimensional array, I'm going to create an outer for loop. I'll use variable d that loops from 0 to 9. This represents the row. So for each digit starting from digit 0, I need to loop through the 7 columns that represents the segments. So to access column 0 to 6, I'll use the array digits at index d as the row and 13 minus I as the column. And that's all that we need to do. After displaying digit 0, I'll pause for 1 second before it loops back and increment d by 1. And repeat the same process to display digit 1. This nested for loop will finish once d reaches 10. But since this code is inside the void loop, it will be repeated again and again and again. Let's upload the code and check the output. Arduino is a simple microcontroller-based platform without a concept of operating system. This means that only one program can run in Arduino at a time. But even though there is no operating system to manage multiple tasks, we can still achieve the concept of multitasking, which means we can implement complex projects involving several components like Sevensegment Display, switches, sensors, motors, LEDs, servo motors, etc. to perform multiple tasks simultaneously. In order to handle multiple tasks in Arduino, you need to understand the concept of millis. To understand millis, consider the following illustration. Let me add a push button switch to our existing circuit. I'll use a 10 kΩ pull-up resistor here and use the digital pin 2 of my Arduino. Suppose that I want to reset our digit counter to 0 when I press this button switch at any time. Using our current program structure, you might do something like this. Remove the local variable declaration d inside the for loop and place it outside, making it global. And then, after this nested loop, I'll check if my digital pin 2 is pushed to the ground. And if so, I'll reset d to 0. Let's upload the code and see what happens. Notice that even if I press this switch, nothing happens. I intentionally placed this if statement after this nested for loop for you to see that this if statement will not be executed until such time this nested for loop is done executing. The main culprit here is not actually the looping statement, but the delay function. When you use the delay function in Arduino, you are actually putting the processor in a busy state or on hold for the time period specified in the delay parameter. During this time, the Arduino processor cannot do any other task like read signal from a push button, for example. And if you want to achieve multitasking in Arduino, you have to get rid of the delay function and start using millis instead. To illustrate it, I'll remove this outer for loop and use this void loop instead. I'll declare two unsigned long variables named startTime display with initial value of 0 and interval display set to 1000. Inside the void setup, I'll configure my serial monitor, then inside the void loop, I'll create a local variable, currentTime, and store the millis return value. Whenever we call the millis function in your program, it returns the time in milliseconds from the moment the program started running. Millis is a time-keeping function that starts when the Arduino is powered on, or reset. For you to see this, I'll use the serial.print line to display the current millis in the serial monitor. I'll comment this code first, and then let's upload the sketch. Then, I'll open my serial monitor, and as you can see, it started counting upwards, returning the current time in milliseconds since the program started running. So, how do you make use of this current time in milliseconds? I'll uncomment this code, and then I'll check whether the current time, when subtracted with the starting time, which is initially started at 0, is it already greater than or equal to the time interval? This is actually the elapsed time that will act as our delay. In other words, this statement simply asks if it is already time to perform the task, by which, in this one, to display a digit to our 7-segment display. And this will only happen after every 1000 counts or 1000 milliseconds is specified in our interval variable. Now, since I removed the outer for loop here, I will manually increment this variable d so that it can access the next digit after every loop. And then, the next important part of this code is to set the new starting time, which is the current time, during the time that this code block is being executed. This ensures that every time you attempt to subtract the current time with the starting time, this if statement will be true when it is already equal or greater than the interval, which is 1000 milliseconds. Now, let me just add a logical operator here and check whether variable d is already 10, and then it can be reset to 0. Let's upload and validate the output. As you can see, we still achieve the same digit counter at 1000 millisecond interval for each digit without using the delay function. More importantly, without using the delay function, we can perform multitasking. You will notice now that when I press the push button switch at any time, our code responded to reset the content of variable d to 0. So, to further illustrate the concept of multitasking, I will be adding another component to control simultaneously. I'll take this opportunity to discuss how to work with a servo motor. Servo motors are self-contained electric devices that rotate or push parts of a machine with great precision. Servos are found in many places, like from toys to home electronics to cars, robotics, and airplanes. If you have an RC model car, drone, or helicopter, then you are definitely using at least a few servos. So, how do servo motors work? Servo motors are controlled by sending a PWM or pulse width modulation signal to the signal line of the servo. The width of the pulses determine the position of the output shaft. When you send the servo a signal with a pulse width of 1.5 milliseconds, the servo will move to the neutral position, which is 90 degrees, the minimum, which is 0 degree, and the maximum, which is 180 degrees. This typically corresponds to a pulse width of 1 millisecond and 2 milliseconds respectively. Note that this can vary slightly with different types and brands of servo motors. Many servos only rotate through about 170 degrees or even only 90 degrees for some. But the middle position is almost always at 1.5 milliseconds. Servo motors generally expect a pulse every 20 milliseconds or 50 Hz, but many remote control servos work fine in a range of 40 to 200 Hz. Although most RC servos are from 180 degree variety, which means they can only rotate in a range of 0 to 180 degrees, however, Continuous rotation, or also known as 360-degree servo motors, are also available. For this demonstration, I am going to use the SG90 microservo, which can rotate from 0 to 180 degrees. So, how do we connect a servo motor to the Arduino? Wiring a servo motor is very easy because you only need to connect 3 wires: the power, ground, and the signal. The power wire is typically red and needs to be connected to the positive 5 volts. A microservo like this, SG90, consumes around 10 mA when it is idle, and 100 to 250 mA when rotating, so you can power it directly with the 5-volt output of the Arduino. The ground wire is typically black or brown and should be connected to the ground pin of the Arduino. The signal wire is typically yellow, orange, or white, and it can be connected to any of the digital pins of the Arduino. In this case, I'll connect it to the digital pin 6. To control the servo motor, we will be using the servo.h library, which comes pre-installed with the Arduino IDE. Then I'll create a variable of type servo I call servo1. In the void setup, we need to tell which pin is assigned to this servo1 variable by calling the attach function, in this case pin 6. Then, to position the servo to a specific angle, just call the right function and pass in the desired position. In this case, I'll pass 180 degrees. Let's upload the sketch and see what happens. And there it is, your servo moves to 180 degree angle. Let's try changing the angle to 90 degrees. Upload the code again. And there you have it. One last try. Let's try changing the angle to 0 degree and upload the code again. And that's it. Now let me write these 3 different positions, 0, 90, and 180 degrees sequentially. But for the meantime, I'll use the delay function of 1000 millisecond waiting time to set each position of the motor. I'll upload the code again, and now, what have you noticed? Even though the servo motor and the digit counter work, but they don't execute simultaneously based on their expected time of execution. After one digit count, the motor must finish the position from 0 to 90 to 180 degrees, consuming 3000 milliseconds first before looping back to perform the displaying of the new decimal digit. So, in effect, our digit counter is no longer counting up at an interval of 1000 milliseconds, but rather, its execution is put on hold until the 3000 millisecond delay is finished. Before I integrate the concept of millis here, let me modify the code for servo positioning. Instead of jumping from 0 to 90 to 180 degrees, I'll create a for loop to change the position of the servo motor, starting from 0 degree to 180 degrees, incrementing 1 degree every 10 milliseconds. And then, I'll copy this entire for loop and change the servo position starting from 180 degrees down to 0 degree, decrementing 1 degree for every 10 milliseconds. I'll upload the code, and as you can see, a smooth sweeping effect of the servo motor from 0 to 180 degrees and vice versa. But then again, this doesn't change the problem that we faced before when dealing with multitasking. You will notice that the program must first finish one complete sweep of the servo motor before it loops back to increment the digit counter. I'll change the servo motor delay and make it 20 milliseconds so that you can see that this greatly affects the digit counter, even though this one uses millis. So now, if we want to accomplish multitasking, meaning the servo motor, the switch, and the 7-segment display can execute its operation independent of the time from each other, we must not use the delay function, but instead, we'll use millis. I'll declare 2 additional variables that hold the start time and the interval time for the servo motor. I'll set the interval to 20 milliseconds. I'll also declare another variable, servo angle, and set it to 0. I'll remove this for loop that controls the position of the servo motor, and then I'll replace it with a condition similar to the one that we use in the digit counter. I'll check if the current time when subtracted with the servo start time, is it greater than or equal to the servo interval, which is 20 milliseconds? Because if it is time to move the servo to the position specified by the servo angle variable. I'll use this servo angle variable, which I have initialized to 0, and increment it by 1 after. Then, I'll check when it reaches 180 degrees, I'll reset it to 0. Now, don't forget to set the new value for the servo start time, which is the current time, so that this code block gets executed after every 20 milliseconds. Let's upload the program and check the result. And based from what we have observed, the servo motor and the 7-segment display execute simultaneously and independently. The servo rotates at an interval of 20 milliseconds for every degree, and the digit counter counts from 0 to 9 at an interval of 1000 milliseconds. And the switch can be pushed at any time to interrupt the digit counter and reset its value to 0 without affecting the servo motor's operation. We can try reducing the speed of the motor's sweeping to 50 milliseconds. I'll upload it again, and as you can see, the servo is a lot slower, but the digit counter still counts every 1 second. Let's try changing the servo's interval to 100 milliseconds and test it again together with the switch. Now, let's try changing the 7 segments time interval and set it to 300 milliseconds. I'll upload it one more time. And there you have it. The digit counter counts every 300 milliseconds while the servo motor still rotates at a slow rate of 100 milliseconds per degree. Although working with millis is a lot to take in at first in comparison with the delay function, which is a lot easier, but you'll get used to it. If you can understand this concept very well, you will no longer be using the delay function for most of your tasks that require simultaneous execution. And now, for your code and circuit connection challenge, I challenge you to create a similar prototype consisting of a 7-segment display, a switch, a servo motor, and an additional 2 LEDs, green and red. The digit counter counts down from digit 9 to digit 0, while the servo motor rotates synchronously from 0 to 180 degrees. As the digit counter counts down and the servo rotates, the green LED blinks at 500 millisecond interval. When the operation resets, either by pressing the switch or reaching the count to 0, the red LED turns on, and repeat the process again. And again, thanks for watching. If you learned something of value here, please click the like and subscribe button for more programming and circuit tutorials. This is Joe Edgo, and hope to see you in the next video lecture.